Welcome to 8.4. So this section in chapter 8, we're going to talk about modular arithmetic and a little bit of its applications in cryptography. I'm actually not going to put a ton of that because that's a lot more that goes into the cryptography class. And your textbook is pretty light on explaining why things work. It just kind of hand waves at a bunch of it. So we're going to focus on, first off, what is modular arithmetic? Why is it cool? But to give the basic explanation, I will just still use cryptography because many of you have actually used modular arithmetic without realizing what you were doing. So in cryptography, we have something called plain text. That's the normal form that something's in, and then ciphertext. And that doesn't mean it has to be in word form or something else. We have an encryption process that changes it from a plain text to an encrypted text. And then we have to wait to decrypt it. So these are functions. You want to think about it because we have to put something in and then take it back out. Not only that, they must be invertible functions. So further, the most basic of all these is something called the Caesar cipher. Truth is, it's not necessarily known if it was really used by Julius Caesar. That's simply what there's a lot of discussion about that. And so it's usually credited him, but it's not really true. The idea was simply that each letter translates to another letter by shifting it by a certain amount. So often, many of you may have done this by simply X moves to A, Y moves to B, and Z moves to C. Or another way to do that is if I assign the letters A is 1, B is 3, and so forth, this kind of ends up working. And then I can say, what if I add 3? Well, mod 26 is where this is going to end up. So let's just to show you what this would look like. Initially, all my letters are here. And so C minus 3, so my message, so to encrypt it, I just take my message and I add 3. To decrypt it, I subtract 3. So like if I was given an A, when I encrypted it, it would move 3 over, so it becomes D. If I was given a D, it moves 3 back and becomes an A. So just to give you an idea about how this works, let's look at these simple messages. How are you? So again, let's go back here and let's look at the first one. So our message would be down here. How are you? And it's easier if we do it on this screen so you can actually have this as a reference. Now notice I'm not using a question mark, but the H, so the H is an 8. So I'm gonna write 8 instead of, I could write 0, 8. O is 15 and W is 23. I'm just going to do this to illustrate. The 8 becomes 11, the 15 becomes 14, and this becomes 26, which again, that means this is K. This becomes, oh, sorry, this should be 18, not 14. This should be R, and this should be Z. So when I send the message, I'm going to send KRZ to someone to decrypt. Similarly, the A would move 3 spots, so it would actually become a D. R would become a U. E would become an H. Y would become, well, we said this before, it becomes, so it's here, it goes 1, 2, 3, so it becomes a B. We already did O, it's R, and U is 21, which becomes X. So this right here would be my message that I would send. This is the encrypted message. So we could send this. It's really nice. It's really easy. Now to undo this, we're shifting back 3 letters, except we're going to wrap this around. So if I had B, it goes back 1 and then shoots back here to the Z's. And that's the key difference about these sort of things, is that this is a kind of a giant ring that I'm going around. And I'm using that terminology because actually there is something in math called a ring. And this structure, modular arithmetic, actually is part of that. But there's much more properties necessary to be a ring besides just this, it rotates around the outside. But let's just come back to this. L, we'll go back 3 letters before, and again, we would work on. So again, to show this one, L is 12, D is 4, and so forth. So I move them back. 12 becomes 9, which is an I. 4 becomes 1, which is A. 16 becomes 13, which is M, and so forth. So actually I send back, I am fine. So this is the idea of Caesar ciphers. And the truth is we're doing this modular arithmetic where we're shifting all of them by a singular amount. That's the most basic. And to be honest, this cipher right here is totally useless. It was outdated by the 1500s. Like there was really easy ways to completely destroy this with brute force. It's not even hard. So before computers even came around, this cipher was dead. But it's a good way to kind of illustrate the idea of modular arithmetic. So let's talk about what does that mean anyways. So your book has this technical definition. And the one that I'm actually going to focus on is actually both 1, 2, and 3. 2, this one right here for 2, this happens to be the idea about how we write this. We write that they are equivalent. Notice, just real quickly, that I'm using equivalence, or congruent is more correct, is 3 straight lines, not 2, 3. Now, I can say that they are equal if they're actually equal. So in modular arithmetic world, then they are congruent in non-modular arithmetic world. Now, modular arithmetic is really, really nice because essentially what I'm saying is when I divide by n, so A and B have the exact same remainder when I divide by n. So let's kind of look at this a little bit more and let's talk about it more. So this whole idea is about having a smallest possible quotient. So if you take any number, if you take any integer, I should say, it's equal and divide it by another number q, there's always going to be a remainder that's between 0, could equal 0, and has to be less than n. You did this in elementary school when you did long division. You always end up a remainder that was 0 or something else. This idea is that remainder, or residue as we will call it, is actually the critical concept of modular arithmetic because it's all about this. Ironically, division does not exist. So while we think about this as division, really it's not division because you're not dividing by anything. You're saying, what's the biggest multiple of Q so that I have a remainder that's within these bounds? Because division does not exist in modular arithmetic. I'm going to echo that multiple times. It does not exist in modular arithmetic. Do not start dividing. It will not be okay. This is a major point that students have to understand and why modular arithmetic is actually hard, and it's used for cryptographic reasons. So we call the least non-negative residues or simply the residues mod n, are again the set of numbers that are from 0 to n minus 1. Those are all the possible remainders. If we think about doing long division, the idea. Now, long division really is the idea of long division is trying to pick something, and you're really guessing, and then you're doing something else. So that's not how your computer does division, by the way. So long division is really a valuable idea to understand congruence because you actually did it. So all of the congruences, we write them as this A with square brackets around them. That is all the possible values that are congruent to A mod n. So let me give you a quick example of this. So suppose that that n equals, let's say, 10. And I want to go, let's say A equals 1. Well, then the box A, the residue, is going to be the set, and just some of these values would be 1, because 1 has a remainder of 1. 11, 21, 31, and so forth. Over here, the interesting part is then it's negative 9, negative 19. Now, why is it negative 9? Because negative 9 is equal to 1 plus 10 times negative 1. So it's not negative 1 because notice and then if you start looking at this list, each of these are 10 apart from each other. So the way often you can create it is simply find your A and add whatever your mod is forward. And then you can see what some different values are in here, but that's the idea behind how this works. So modular arithmetic, again, and by the way, please do not, I'm going to tell you all, do not use the Python or C way of writing modular arithmetic where you do a percent. We're not doing that. We're actually doing modular arithmetic, and I expect you to use the mathematical notation. So let's talk about a little bit more about modular arithmetic. So the fundamental fact about it is that the following skills are completely possible: addition, subtraction, and multiplication. Notice, and I'm going to note this, no division. Do not get lost on that, okay? And the reason for that is because what is subtraction? Subtraction is really adding a negative version of a value. Therefore, it's still addition. What is multiplication? It's repeated addition. So all this comes down to the fact that addition is modular arithmetic. And the way modular arithmetic, this is the cool part about it. So suppose I want to find 5 times 8 mod 3. I can first do 5 times 8, and that gives me 40, which is equal to 39 plus 1 more. So it's congruent to 1. So this thing, I could have done this by gotten a really big number. These could have been even bigger, and I could have gotten another big number. So that's the idea is I'm like, it's not good. However, I could have done 5 mod 3, which is going to give me 2. And then 8 mod 3, which would have given me also 2. Because 5 is 3 plus 2 left over. And this one is 2 times 3 plus 2 left over. So that's how we got both of these 2's. 2 times 2 is 4, which is 1 mod 3. And this is the idea that actually permeates and allows us to do a lot of really cool things with modular arithmetic, is that we can actually break down computations into smaller bits. So in general, here are the 4 major properties to understand about that. If you give me any value and I know what it is mod n, and another value, I know its value mod n, then their congruence, a plus b, is equal to their congruences mod n. Same with subtraction, same with multiplication. And then the interesting part is if a is congruent to c mod n, I can raise both them to the same power. That one is particularly interesting for some really great examples, but let's do one and let's practice this just a little bit. So let's come here and let's try this example. So I want to find what's 55 plus 26 mod 4. So I'm doing all these mod 4. Well, I can start off here and say that 55, trying to understand why this is true. Well, 55, as it shows up here, 55 is equal to 52. And I don't like it when they do this minus stuff. That doesn't make more sense. It actually is actually more correct that this is equal to 52 plus 3, and 52 is equal to 13 times 4. So this is a multiple of 4 plus 3 more. That's why 55 becomes 3. So because we've established that 55 is congruent to 3 mod 4, then the 55 becomes 3. 26, which is 24 plus 2 more. So this is where knowing your multiples really helps you out, is 2. Then this is just going to give me 5 mod 4. On the other hand, if I did this side over here, if I add these together, that would have given me 80, because 81. And the reason you get that is 5 plus 2 is 70, but the other one's 11, so you end up with 81. But 81, quick reminder, mod 4 is 20 times 4 plus 1 more, so that's congruent to 1 mod 4. This, on the other hand, is 5. So that's 5 mod 4, which is congruent to 1 because it's just a remainder of 1. It's just 1 more than 4. Which one is easier computation? Often, for many people, the easier computation is to take this and go to its smaller values real quickly, because then you're dealing with smaller numbers. But again, it depends on the person you're dealing with and what they see. So just to show more for part B, subtraction, again, if we actually did the actual subtraction, this is 29, but 2 minus 3 minus 2 is 1. 29 is 28 plus one more. So that's why it's congruent to 28. And so we have that. What about when we multiply them? Again, this is a really nice, this is where I think it comes in really nice is multiplication and exponents. Because you could have done this and then found this. This is a really big number to try to find mod 4. But 3 times 2 is 6, which mod 4 is 2. Well, it turns out that this is actually congruent to 2 mod 4. And there's lots of ways to have gone through that. They did it as 6. I don't know why, because again, you actually would want this value right here to be between 0 and n minus 1. So this actually should be 2 mod 4. I'm just showing because your book does this. I don't know why. I don't really like it. Now, on the other hand, this one's even better because we're doing things mod 4. 55 squared is 3,025. Now, the nice part is any thousands. So I'm just going to write that. The nice part is 3,025. I can write that as 3,000. And the good part is anything that's times 100, it's any multiple of 100. So it has at least 2 zeros on the end is always a multiple of 4 because it's 25 is times 4 will give you 100. And then you just multiply that times whatever's left to get there. So this is easily, if I can factor out 100, I can factor out a 4. So this is 4 times something. What? I don't really care. But plus 25, and 25, we can break that up into 24 and 1, which this is 6 times 4, which means there's your remainder for this huge, nasty thing. On the other hand, 3 squared is just 9. That's really easy to know that 9 is congruent to 1 mod 4 because we turned it into a smaller number. That is actually the bigger power and the idea behind how we do a lot of this stuff that's critical. So let me show you a little bit more about why this is really cool and valuable. Let's talk about modular arithmetic for a second. So if I want to multiply a times b, I can simply take their mods, I can take their congruences and multiply the congruences together, and then take that again mod 4. Same with the power, I can do that. So this idea of this corollary, where I'm gonna have to do mod, is actually the idea of where we're gonna go. And this is why when I wrote this down, these things got a little bit better. And we are gonna use the floor function. That's essentially what it's using. But again, I'm not gonna give you problems. You're not gonna have a calculator on the exam. So doing your best to understand these concepts actually makes the process even easier for you. So again, if you have this thing, I would say, what is 55 mod 4? Okay, that's 3. What's 26 mod 4? That is 2. And work my way from there and kind of come back to this. All right. Now, there's another really cool idea, and this is the idea that's the basis of not just RSA encryption, but a lot of encryption, because a lot of encryption uses exponents. So we actually use an idea that's 2 exponent processes that should make sense. First off, if I say x to the 2a, I can break those apart because the rules of exponents. As a quick reminder, in case you forgot, x to the ab is equal to x to the a, all that to the b power. And I get to decide which one's which because multiplication is commutative. So I can pull the 2 on the outside. So why is this useful? Well, it's because then we use another exponent rule. And yes, this is why exponent rules, you learned all these algebraic concepts. Now we understand why they're super useful as we go on. The other one is this. The product of these things is this. So x to the a plus b is equal to x to the a plus x to the b. So what's that mean? Well, it means let's take 7. 7 equals 4 times 2 times 1, which is x to the 4th. X to the 4th times x squared times 1. Well, what I can do then is to find x to the 7th is I can find x to the 4th. That's easier. And x squared, and then I can take x to the 1st. Or I could do something even cooler. If I know x, so let's say x, let's do an example here. Let's say I want to find 3 to the 7th power mod 9. Actually, I don't want to do 9. Let's go mod 8. Well, we know that this is going to be 3 to the 4th mod 8 times 3 squared mod 8 times 3 mod 8. Okay, 3, that one's easy. This one is 9 mod 8, which happens to be 1. Okay. Now, before any of you start going crazy here for this one, doing 4 times 4, I mean, because you can actually do 3 times 3 times 3 4 times. Better way is that realize that this is 3 squared. So wait, what was 3 squared mod 8? It was 8. I mean, it was 1. So this is 1 squared mod 8, which is just 1. So in reality, this thing is congruent to 1. Because you're going to, I'm sorry, not 1, 3. Because you're going to get 3. We're going to end up with 3 times 1 times 1, which is 3. So that is why this becomes super powerful. And this thing that we do right here is known as the binary expansion. And we can then, because if you take 7, and again, going back to earlier in the class, what is 7 as a binary number? Well, in base 2, 7 in base 2 would be, I need 1 to the power of so it would be 1, 1, 1, because that is 2 squared plus 2 to the first plus 2 to the 0 power. So the binary expansion actually tells me which things I actually need to take and how we utilize all those ideas. So this is actually then relates back to why we did binary expansion earlier in the semester. All right, let's look at another example. So I want you to try this one. What's 144 to the 4th power mod 713? Go. All right, so hopefully you're back, and hopefully you did not just raise 144 to the 4th power and then take it mod 714. Well, that would work for this. That doesn't really work as those powers get big, our numbers get big. Most computer systems, like we're dealing with in cryptographic, like 10 to the 26th digits. So massive numbers. And we're raising things to powers that are crazy huge. So we don't, that process is absolutely junk. Instead, a better way to do this is raising this to the 4th power, remember, is 144 squared. So I start off with, let's just take 144 and square that. That's going to give me this, which mod 713 is 59. I then square that, and it gives me this, mod 713 is 629. So because I simply did this by squaring each step, it became so much easier than if I had tried to break it down some other way. All right, so let's move on to another concept. It's known as the extended Euclidean algorithm. And now, before I get to why the extended Euclidean algorithm, the Euclidean algorithm is this idea that, remember, is a way to actually find the greatest common divisor. And it's a wonderful version, and we're going to do what's called the extended version of it. Again, you can handle this. It just requires you to work through some steps and understand the process. This is really critical because of let me show you a different problem. So if I did the problem, 3x is congruent to 5 mod 7, how would we answer this question? See, if this was normal numbers, you would divide both sides by 3, but that is actually does not exist because we can't divide in modular arithmetic. The only way to solve this problem is two ways. Either use this or brute force. And to be honest, in this case, brute force is not too bad because all I have to do for brute force is literally do 3x, and then I'm gonna do x, and I'm gonna do those mod 7. So let's all the x's possible are 0, 1, 2, 3, 4, 5, and 6. So I have only 7 values to run through. 0 times 3 is, well, 0. That's not it. 3, no. 6, no. 3 times 3 is 9, which is 2 mod 7. 3 times 4 is 12, which is 5 mod 7. So, hey, we have a winner. Ding, 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 ding. Okay, that really didn't help a whole lot. But, and then 5, just to help point out, is going to be 15, which is congruent to 1. And then 6 times 3 is 18, which again is 4. Now notice, so in this case, x equals 4. Well, that was nice. Since it was mod 7, I only ran through 7 options. What if I'd done the previous example was mod 713? I now have to run through 713 different possible values. Okay, what if it's a massive mod? Now I'm in a really bad spot. It's not okay. We don't like that. Because it's essentially trying to do a linear search on something, which is really inefficient. I'm just telling you, it's not good. So we use what's called the extended Euclidean algorithm. So the idea behind this is this. I want to find a linear combination of two numbers, a and b. And if that exists only if there's integers s and t where they equal d. So d is a linear combination of a and b. If there exists some s and t, could be more than one. In fact, it's either usually infinite or does not exist. Secondly, we need something called the greatest common divisor. Remember, that is the greatest common divisor. If this greatest common divisor right here, if d is equal to the greatest common divisor, then this exists. And in fact, if d is a multiple of the greatest common divisor, then this exists. So there's lots of ways to go on and talk about this and utilize this. So let's look at how this works exactly. So we are going to start off by just doing the Euclidean algorithm to find the greatest common divisor of these two things. Because again, if I ask you to find the greatest common divisor of 330 and 156, many of you might do something like this. You got two options. You start just checking numbers, or you go 330. How many of you do something like, well, that's 2, and let's see that be 165. And then I can see that this has a 5 in it. If I pull out a 5, let's see, that's 15 and 15, so that's 55. Oh, no, 33. How bad. I miscalculated that. That would be 33. And 33 is 3 times 11. All right, now with prime numbers. Now if I come over here to 156, well, clearly a 2 goes in it. Take 2 out of that, and you're left with 78. What numbers go in here? Well, you can sit there and practice a couple things, but if you know 7 plus 8 is 15, I know that 3 must go into it. So because that's a multiple of 3. That's called the rules of 3 in case you don't know it. Anyways, this is then really nice. If you divide this by 3, you're going to get 23. Nope, 26. My apologies. I was like, that doesn't work. 26. Can't read my own notes. All right, but notice both of them have 2 and 3, 2 times 3. Boom. The problem with this is you just had to do a prime factorization of both these problems, which I will tell you is a horribly not efficient process in general, especially as numbers get big. So all those things you did in grade school, really useful. They're actually really, really cool tools. They're just really hard to duplicate on the high scale. So that's why you did them on very small, and you have to understand it because you have to understand the complexity because computers just can't do it on their own. So the way we do this instead of the extended Euclidean algorithm, we take the bigger number. And what we're going to do is we're going to write the bigger number. This is where this gets fun. We say this as the bigger number, so 330, is equal to what times 156 plus what? Well, you could check and realize that I can do 2 times this, which, by the way, that's going to be 312, which leaves a remainder of 18. Now what I do is I take the 156 and I move it down and I make right 156 equals what times 18 plus what? So notice that I have this, and 156, I'll just help you right now, is equal to 8 times 12. Now I'm going to take those numbers again. I'm going to go 18 equals what times 12 plus what? That's clearly 1 plus 6 more. And 12 equals 6 times 2 plus 0. So when you get a remainder of 0, the previous remainder is the greatest common divisor. So we had to do this arithmetic over and over and over again. And this is what the Euclidean algorithm is doing. And this tells us right now that the greatest common divisor is 6. But so what? How does that help us find the linear combination? Well, I'm going to rewrite those things over here real quick, off to the side. So 330, I'm going to clean this up, equals 2 times 156 plus 18. 156 equals 18 times 8 plus 12, and 18 equals 12 plus 6. I'm just going to start with that. And now I'm going to rewrite actually all of these equations. I'm going to rewrite all of these equations, again, trying to illustrate something. So I can rewrite this top equation up here as, I can rewrite this equation as 18 minus 12 equals 6. Rewrite this equation as 156 minus 8 times 18 equals 12. And I'm doing that on purpose. And I'm going to rewrite this list up here as 330 minus 2 times 156 equals 18. So the extended Euclidean algorithm is going to do this. We know that this whole thing right here is equal to 12. So I'm going to substitute that in. So I get 18 minus parentheses 156 minus 8 times 18. And I'm not multiplying these out on purpose. I'm leaving them. When I distribute, that's 18 minus 156 plus 8 times 18, because the equals 12. And now notice I have, between these, I have 9 18s. So I have 9 times 18 minus 156. Sorry, not equals 12, equals 6. That's my bad. Let me erase that real quick. As soon as I wrote that, I should have caught it. So these are equal to 6. Equals 6. But going back up here, this whole line right here is equal to 18. So I can substitute that in. So I get 9 times 330 minus 2 times 156 minus 156 equals 6. Well, if I multiply these together, I get 9 times 330 minus 18 times 156 minus 156 equals 6. But I can combine like terms right here, and I'm going to end up with 9 times 330 minus 19 times 156 equals 6. And as a result, the linear combination, my number here is 9. That's my number. But the number here is negative 19. And that is the critical idea, that those are going to turn out to be our ideas. All right. So let me clean this up and show you a cleaned up version of it. So we did all this and we got this nice greatest common divisor. The greatest common divisor is equal to a linear combination of those values. And it's always going to be true. And so this always is true. And that is actually critical for us to find the inverse of modulo n. Now, what is an inverse? Well, this goes back to just an idea. And the notation is actually critical for you to understand. So an inverse is something that when I multiply it together, so inverse of A is a number that's going to give me 1. So going back to real numbers for a second, I'm going to just put this down here on the bottom. In the real number world, 2 times what is equal to 1? Well, hopefully you're all thinking it's 1/2. That means that 1/2 is the inverse, the multiplicative inverse specifically, of 2 in the real numbers. The problem with that is, what if I'm not in the real numbers? Then this 1/2 doesn't exist. But we dealt with this just a little bit, so it becomes a little bit harder. So let's go back to a different example real quickly so I can just kind of demonstrate an idea. So if I'm asking again, 3 times what is 1 mod 8? What I'm really asking here is, what this question is the same thing as what is the inverse of 3 mod 8? So that is our question here. So we have to solve it by actually figuring out this, the linear combination. And then if I'm taking mod t, then I can kind of work through this. So if two numbers are relatively prime, meaning their greatest common divisor is 1, then this works down here. So you have to kind of be cognizant of that and kind of utilize this to our advantage. So let's practice. Let's kind of explain this a little bit more. If you have two integers a and n, where their greatest common divisor is 1, then a has an inverse mod n. More specifically, it'll have. Now, notice this doesn't mean that if the greatest common divisor is not 1, that they do not have an inverse. That's kind of an important thing. So 2 questions I could ask based on this is, find an inverse of 43 mod 660. In other words, I want to find S such that 43S is congruent to 1 mod 60. Similarly, I want to find the inverse of 3 mod 40. So let's go to the first question. If I ran through the example and actually did the calculations on this is from an example in your book, then the linear combination gives me this. What does that mean? So this is congruent. So notice that 307 times 43 is equal to 1 times 660. When I take mod 60 of both sides of this portion right here is going to go away, and this becomes just the 1, because remember, any multiple of 60 is going away. So this is just going to be 307, which so 307 is the inverse of 43 mod 660. And again, the way to find that is doing that extended Euclidean algorithm. That's how we do it. So let's come to this one. So we'll find a linear combination of 340 that equals 1. You could do guess and check, or what you can do is this: 40 divided by 3. So we get this is equal to 3 times 13 plus 1. By the way, once you get to a 1, you know the next one is going to be a 0. So the greatest common divisor is 1. And so we have this linear combination right here, actually, of 40 minus 3 times 13. What does that mean? Well, it means that literally 3 times negative 13 is equal to 1 plus negative 1. So I just took this and moved it over to the other side. When I take mod 40, 3 times negative 13, but I don't want negative 13. So often the easy way to know what is negative 13 mod 40 is simply to do, so negative 13 mod 40 is really the same thing as 40 minus 13, because isn't this 0 minus 13? And isn't 40 congruent to 1 in terms of mod 40? So this is just, what's 40 minus 13? It's 27. So again, this is why we have these ideas. We're building on this, reading those ideas out. All right. I want you to play with that. I want you to feel comfortable. Let me know what questions you have, and good luck.